You may be familiar with the intuitive definition of winding number. The number of times a loop L circles a point P. In this case, the answer is 2. Mind you, the winding number depends on the position of your point. About this point Q, it's only 1, because Q's outside this inner loop, so this bit contributes nothing to the winding number. Also, the direction of travel is important. In these two cases, we're circling the point anti-clockwise. If instead we circle clockwise, we attach a minus sign to the winding number. Here, the loop M circles the point R once in the clockwise direction, so the winding number is -1. Notice again that we have a redundant loop. This little bit here doesn't circle R at all, so contributes nothing to the winding number. Well, that's the intuitive idea of winding number. The first thing we're going to do in this program is to develop a rigorous definition.
In fact, this is going to take a number of steps. To start with, we have to say what we mean by a loop, because we mean more than just a closed curve. A loop is in fact a continuous function L from an interval AB to the plane R2, with L of A equal to L of B to ensure we get a closed image curve. You could think of the point T as representing time. Then, as T increases steadily from A to B, the image point traces out the curve. Of course, there are lots of possibilities for the function. The speed may vary. You could go back and forth for a bit, and you could even have the curve traced out several times rather than just once. These details could obviously affect the winding number. That's why our definition of loop involves a continuous function rather than just its image curve. Right. Now for the definition of winding number. If we consider a ray from the point P to each image point of L, then what we want to count is the number of revolutions swept out as T goes from A to B. So what we do is to take a circle C, the center P, and we record the directions of the ray by the points where it intersects the circle. And we count the number of complete circuits made by the intersection point.
So we've actually defined another function, Q, from the interval AB to the circle of directions with QA equals QB. And because L is continuous, then Q is also. Then our rigorous definition of winding number in terms of Q is that it's the net number of revolutions of Q of T as T goes from A to B. We have to take net revolutions because, for example, if Q went once round the circle clockwise, then once anti-clockwise, we would want a net result of 0 revolutions as our winding number. So what we need is a way of keeping track of the net revolutions as we go round. In real life, there are lots of devices which effectively do this. The net revolutions of a nut on a screw thread can be determined by the vertical distance travelled up or down the thread. To record this, just mark the starting point. Then, whatever the nut does, wait until it stops and measure the distance from start to finish. For a mathematical version of this idea, we replace the nut on the thread by a point on an infinite spiral. Then, to get the movement of this point, we project the spiral onto our circle of directions, and we move the point on the spiral, keeping exactly in step with the point on the circle. In this particular example, the point on the circle makes 2 net revolutions, so we'll get 2 turns on our spiral. So, our winding number gets recorded on the spiral as the number of full turns between start and finish. To write this down as a formal definition, we reintroduce the interval AB.
The position of the point on the spiral can be expressed in terms of a third function, q hat, from the interval to the spiral, with A and B mapping to the start and finish. And since our infinite spiral is just a twisted version of the real line, we can express the number of turns as a distance. We'll take one complete turn as our unit of distance, counting +1 for each turn upwards and -1 downwards. Then our winding number is just the distance between q hat A and q hat B. Mind you, if q hat is not continuous, this definition might give the wrong answer. For example, say you had a q hat which started off above q, going continuously round the spiral, but then it jumped suddenly, missing out 2 full turns. It would still be keeping vertically above q, but this formula would overestimate the winding number by 2. That's why we insist on a continuous q hat. In elementary treatments of winding number, the step that's usually missing is effectively the proof that a continuous q hat exists. So, finally, that's what we'll prove to complete our rigorous definition. To start off, notice that the spiral can be thought of as a covering space of the circle C. In other words, the projection P is a local homeomorphism. Remember what this means. If you restrict P to a small region of the spiral, this restricted P is a homeomorphism and therefore has a continuous inverse. And that's what we'll use to construct a continuous q hat.
Here's how we do it. We've shown the interval AB subdivided into a finite number of pieces, each piece small enough that it maps only to a part of C, say not more than half of C. The proof that there is a finite subdivision that does this is not difficult, and you can look it up later. So let's assume that the interval Tn plus 1 maps to this thick segment. Upstairs, the part of the spiral that lies over that segment is in separate pieces, each one homeomorphic to the segment downstairs. Now let's construct a continuous q hat. First, we fixed our starting point, q hat of A, by choosing one of the points over q of A. Now we use proof by induction. We first assume that we've already constructed a continuous q hat on the first n pieces, A to Tn. I'm going to show how to construct it on the next piece, Tn to Tn plus 1, so that it stays continuous. Concentrate on the segment upstairs containing q hat of Tn. The map P restricted to this segment is a homeomorphism. Call it P bar. And we use the continuous inverse of P bar to define q hat. First, map T to the circle by q, and then map q of T up to the spiral by P bar inverse. This gives a continuous q hat on this subinterval because both q and P bar inverse are continuous. Now we use the glue rule. Q hat is continuous on the intervals A to Tn and Tn to Tn plus 1, and its value at Tn is the same for both intervals. So it's continuous on the combined interval A to Tn plus 1 by the glue rule. Notice that there's no choice about q hat on this little interval. We have to start with the value of Tn that we already had. Otherwise, we wouldn't get continuity at the point Tn. So we've extended our continuous q hat uniquely to the interval from A to Tn plus 1. So by induction, we can extend it uniquely to the whole interval from A to B. So we can now be sure that our definition of winding number gives the unique answer that we wanted. The continuity of q hat ensures that the number of turns between the endpoints is a correct record of the net revolutions of q of t. And of course, it doesn't matter which starting point we choose, because a different choice would merely shift the whole thing up or down.
Right. Now for the second part of the program. We're going to look now at what happens to the winding number if you distort your loop. For example, think of this image curve as an elastic band and vary it continuously to get a new curve, L2. We're going to prove that if the loop doesn't cross the point P during the continuous variation, then the winding number doesn't change. Well, that seems obvious in this particular example. But what do we mean in general by the term continuous variation? Remember, a loop is not just a closed curve, but a continuous function from an interval to the plane. We've illustrated that here by drawing several copies of the interval AB, and we're thinking of each copy being mapped by a continuous function to give one of these image curves. So we have a whole family of continuous functions, one function for each value of v between 1 and 2. Then, when we say the loop L1 varies continuously into the loop L2, what we mean is this. If we consider any two numbers v and u which are close together, then for each point t in the interval AB, Lu of t is close to Lv of t. So that's what's meant by continuous variation between two loops L1 and L2. And we give the idea a special name. We call it a homotopy between the loops L1 and L2, or we say L1 and L2 are homotopic. Now let's prove our theorem that homotopy doesn't change winding numbers. We'll do this using our rigorous definition of winding number. For each loop of our homotopy, there's a corresponding map Q from the interval AB to the circle of directions. And the family of maps Q also constitutes a homotopy, because if we consider a loop LV and a nearby loop LU, then since LV of t is close to LU of t, so QV of t must be close to QU of t.
And the same is true of the corresponding family of maps Q hat. This family is also a homotopy because if the images of nearby Q's are close, then so must be the images of nearby Q hats. So a small change in V can produce only a small change in Q hat. In particular, this is true when t equals A and when t equals B. But this implies that the winding number for nearby loops LU and LV is the same. That is, the distance between these 2 points and between these 2 points is the same. The reason these distances are equal is that Q hat of A is always vertically below Q hat of B for each V. So if the distance between them were to change as V changed to U, it would have to change by a whole revolution at least, which can't happen because the endpoints only change by a small amount for a small change in V. So that proves that the winding number can't change in any little part of the homotopy. And this means it can't change during the whole homotopy. To do so, it would need to change suddenly by a whole integer in some little part of the homotopy, and that's precisely what we've just eliminated.
So that's our homotopy theorem. Homotopic loops have the same winding number about a point so long as none of the intermediate loops pass through the point. This elastic deformation is just one type of homotopy. Let's now look at some more. A simple type is just ordinary translation. If we take an image curve L1 and translate it without crossing the point P, then L2 is homotopic to L1 and hence has the same winding number.
Of course, instead of translating the curve, we can get the same effect by translating the point in the opposite direction to the position P dashed. P dashed has the same relationship to L1 that P has to L2. So, we've shown that winding number doesn't change if we move the point without crossing the curve. That is, points in the same region of a curve have the same winding number. Finally, here's a homotopy which gets rid of a redundant loop. This inner loop is contracted down to a point, and this leaves the winding number unchanged. So this example shows that we can replace loops by simpler loops which have the same winding number about a particular point. And we've also seen that if we stick to the same loop, then different points of the same region have the same winding number. But what happens if we cross the loop into a different region? Let's go back to the example you saw at the beginning. The winding number of this loop about Q is 1, but if we cross into the inner region, the winding number about P is 2. Well, a possible rule which would account for those values is this one. If we cross a loop, then the winding number increases by 1 if the loop's traced once from left to right as we cross it. Here, it's traced once from left to right as we cross from Q to P. Of course, if we cross the other way, then the loop's traced from right to left as we cross it, and the number decreases by 1. To prove that this rule always works, we can use our homotopy theorem.
This picture represents the rule we're trying to prove. We've shown a segment of a loop traced once from left to right as we cross from Q to P. And we want to show that the winding number increases by 1. Well, instead of crossing the loop to a second point P, we'll concentrate only on Q and distort the loop to cross Q. Like this. If we can prove that this distortion increases the winding number by 1, that's clearly equivalent to prove that crossing the loop increases it by 1. Well, we can apply a homotopy to this, which pushes these two horns together. The winding number of this new loop N is the same as that of M because they're homotopic. So we just need to prove that this new loop has winding number x plus 1. Well, compare N with L. They're identical, except that N makes one more positive circuit round Q than L does. So N certainly has winding number x plus 1. And that does it. We've proved that if you cross a loop traced once from left to right, the winding number increases by 1. And with that rule, it's now easy to calculate winding numbers about points in different regions of a loop. For all points outside the loop, like S, the winding number is of course 0. Then, when we cross from S to any point R in this region, the winding number increases by 1, because the loop goes from left to right as we cross it. Then, crossing from R to Q, again an increase of 1. And again crossing from Q to P. Now, what about X and Y? Well, in both cases, the loop is traced from right to left as we cross it. So the winding number decreases by 1 in both cases.
Now for the final part of the program, an application of winding number to the study of continuous functions. In particular, we're going to tidy up something about covering spaces. For a regular n-sheeted cover, every point in the base S has n points mapping to it. That is, there are n pre-images for each point of the codomain. But this is not true for branched covers. Remember this picture of a double cover of the sphere with two branch points, one at the bottom and one up here at the top. The base is this sphere, and the cover, shown in two halves, is also a sphere. Because remember, these two dotted edges are identified, and so are these two. So each half is a hemisphere or topological disk. Also remember that the projection is radial projection. Well, this map is not quite 2 to 1. Every point has two pre-images, 2 points mapping to it, except for the north and south poles, each one of which has only one pre-image, the branch point that maps to it. Well, it would be nice if we could say that every point had two pre-images. It turns out that if we use the idea of winding number, there is a sense in which each one of the branch points should be counted twice. first, take an ordinary point and consider one of its pre-images. Now, take a small circle, a small loop that circles once positively about that pre-image. Then the projection is again a loop which has winding number +1 about the point. But if you do the same thing at a branch point, the projected loop will have winding number +2. Consider a loop like this around the branch point. It's traced around here and then continues under here, and you can see the rest of it from the other side. Round here, ending up where it started. Remember, this edge is identified with the top edge. Well, you can see this loop has winding number +1 if you imagine unwinding this shape and gluing the identified dotted edges to get a hemisphere. Then the loop would just be a circle traced once positively about the branch point. But the projection of this loop onto the base is a circle traced twice positively around the North Pole. Think about it. So, this has winding number +2, and that's the sense in which we should count the branch point twice. We say it has a multiplicity of +2, whereas this point has a multiplicity of +1. So if you take account of multiplicities, every point of the codomain has two pre-images. Well, this idea works for any branched cover where the domain and codomain are orientable. Being orientable means we can assign a consistent sense of positive orientation over the whole surface. So we can define multiplicities just as we've done here. Take a loop in the domain which winds positively around the pre-image once, and look at the image of the loop in the codomain. Then the winding number of the image loop about the codomain point is the multiplicity of the pre-image. And there's a theorem called the Brauer degree theorem, which says that every codomain point has the same number of pre-images as long as you count each pre-image with its multiplicity. This number, 2 in this particular case, is called the Brauer degree of the function. In fact, Brauer degree can be defined not just for branched covers, but for any continuous function between closed orientable surfaces. And if each codomain point has only a finite number of pre-images, we calculate the Brauer degree just as we've done here by counting pre-images with their multiplicities. So, the idea of winding number has given us a deep insight into continuous functions. We can now say that two functions which have different Brauer degrees are fundamentally different, because if the degree is n, then the function is characteristically n to 1.